the impacts on lamination quality. So actually, this is a twofold impact. There can either be inhomogeneous peroxide content along an EVA roll, so the raw material that you use for your encapsulation process. It's talking about indentation measurement on such a fragile device like a PV module. One may be scared that we do some damage to the cell. And of course, we were concerned about that in the very beginning. Now the question is how you would apply a measurement like this. Usually when we talk to customers, in the first place, they always ask for an inline method because they want to tell their customers that they do a 100% control. And this is usually quite tough discussion because I'm Christian Camus representing LATEC here with the topic on non-destructive quality control for PV module encapsulation. And yeah, let me just give you a brief outline about the talk. I will give a very brief company overview to tell you who LATEC is. Then I'll briefly cover the motivation and the challenges in Crosslink measurements. I will introduce our tool to give you a basis for the following slides. And afterwards, we'll look at the applications of the Crosslink tool in solar module production. And afterwards, we will also have a glance on how this tool can also be used for the assessment of PV modules with an unknown bill of material. And then I'll end with a summary and we'll go over to your questions afterwards. So let's come to the company. So most of that has been said by Miguel already. So we're based in Berlin. Almost 25 years in the field with roughly 75 employees now. We're part of the Nanomic holding group. And actually, nowadays, there's more than 3,500 systems in the field. And our core business is process integrated, mostly optical metrology for markets like semiconductors, thin film industry, and academia, including lighting, laser, PV, and glass coating. And obviously, today we're looking at the PV application. So the core markets, also as Miguel just said, is epitaxy processes. So LATEC grew big with the introduction of LEDs in the industrial production. Later on, laser and power devices followed. And about a bit more than 10 years ago, we also started to provide inline solutions for functional glass coating and photovoltaics. And again, this is the focus for today. Just very briefly, we're going to look at a metrology method, which is shown, or the appropriate tool is shown here in the center, the LATEC Crosslink tool, which is meant to enable the quality assurance of PV encapsulation by visualizing poorly laminated areas, which would later on lead to failures in the field. The technology behind it, and I will explain that in greater detail in the following, is a thermomechanical probing of the degree of EVA cross-linking in the encapsulation. And obviously, this applies to silicon-based photovoltaic modules, as we're talking about glass backsheet modules. So just very quickly about the impacts on lamination quality. So actually, this is a twofold impact. There can either be inhomogeneous peroxide content along an EVA roll, so the raw material that you use for your encapsulation process. On the upper left here, you can see data from a Ralph Gottschalk group where they investigated the peroxide content for different EVA rolls, which just came off the shelf. And you don't have to take too much attention at the exact scale, but the important message is that it is quite homogeneous and there's several factors in the content along the roll. So if you use that material for lamination, you might suffer from this inhomogeneous distribution by ending up with different distributions in your module itself. The second impact is the inhomogeneous or the potentially inhomogeneous laminator heating profile. Just two examples are shown here, which we will also revisit later on. So they can be either widespread inhomogeneities over a larger area or very detailed and local inhomogeneities that in any case can lead to some poorly laminated areas in your photovoltaic module. And the key thing and the key thought behind all this is that humidity will always find the weak point of your module in the field. So you really want to make sure that there is no weak point. It's not the target to have the majority of your EVA being well laminated, but you really have to take care that all of it is laminated well in order to protect your device. So now let's come to the tool itself. This is the cross-linking tool in its manual operation mode. So it's a standalone tool where the operator can place the module on a roller table to position the measure, or to go to the desired measurement position, and then conduct the measurement just by pulling this handle here. Everything afterwards is completely automated. And then a measurement is conducted, which is completely non-destructive. The test duration is somewhere between 10 and 60 seconds per measurement with a precision up to 3%. It works for all types of backsheet modules with a cross-linking encapsulant, even though it will require a calibration process to really come up with an absolute gel content number. Otherwise, it will just provide a dimensionless number, which you can still use for comparative studies if you always work on the same bill of material. But if you want to have an absolute number, you would have to do that calibration. The tool relies on a method that was originally developed by Fraunhofer USA. It's a patented method, and we're the only licensee. And we're also listed, or the tool is listed as an alternative method in the IEC standard regarding encapsulation testing. So in conclusion, it's a non-destructive method that basically allows you to work completely free of any chemical lab or any chemical waste disposal. Due to the speed of the measurement, you are able to do full mapping of the modules. The method is IEC compliant, and due to the simple handling, it doesn't have any operator impact on the measurement result, which is quite different in the chemical testing. So what's the mechanism behind it? The trick is that we're actually not doing just an indentation measurement as it's usually done in polymer science or any rheological measurements, but that we're doing a thermomechanical one. This means we're heating the sample as it is measured by indentation, and above a certain melting, which is actually the melting point of the pure EVA material, and above this temperature, we do see a clear split up of the storage modulus with increasing or decreasing gel content. So above this temperature, all the mechanical properties are basically determined by the cross-link fraction of the polymer, because everything else is melted and in a quasi-liquid state. So if you want to put it very simple, what we do is doing a spring constant measurement of the heated module. And how is that done? Let's see here. So what we do is we're lowering an indentation stamp on the backside of the module. So we're coming from the backsheet side. Then after this device has been settled down on the module, there is a small indentation stamp that presses some micrometers into the backside of the module. And then this indentation is released after a couple of seconds. And this relaxation process is analyzed kinetically. And from the response, how the material pushes back on the stamp, we can deduce a direct correlation for the degree of EVA cross-linking. And since temperature is very important, the temperature of the module, which is heated with an halogen lamp from underneath, is controlled by a pyrometer, which is incorporated into the measurement head. And this is exactly what I meant by measuring the spring constant of the layer stack by analyzing this bounce back, if you want to call it like that, of this indentation step as the stamp is released. Of course, if one is talking about an indentation measurement on such a fragile device like a PV module, one may be scared that we do some damage to the cell. And of course, we were concerned about that in the very beginning, but we did a lot of tests with different institutes when the tool was developed to verify that this is not the case. So we did cross-link measurements before and measured, applied various methods before and after. So we did electroluminescence, we did a damp heat afterwards for 2000 hours, did EL again, did performance testing, did the wet leakage test, and none of those tests showed any effect of the latex cross-linking measurement. So we think we can really claim that it's a non-destructive, even though not contactless measurement. So now let's come to the sensitivity of the tool. What we can see here is a series, or the results that were obtained on a series of 11 modules that were prepared by our partners with different lamination times ranging from 1 to 10 minutes. So that's kind of the critical regime where you obtain good lamination for, in that case, EVA. Each of the mini modules, which just contained one cell, was measured on 9 different positions. And what you see here on the Y scale is this dimensionless LXM value, which stands for latex cross-linking metric, which scales with the degree of cross-linking. And that this is the case, you can see here. So after about 3 minutes of lamination, we have a sufficient degree of cross-linking so that we do see a clear scaling of the LXM value with increasing lamination time, which means with increasing degree of cross-linking. So particularly in that part, which is critical for production, we're very sensitive and are able to resolve the degree of cross-linking. Now let's look how the tool is applied here by our by Hanwha Q cells. On the left, this is data they published a couple of years ago on the EU PVSec. And what you see here on the left-hand side is the correlation between the LXM number ranging from roughly 1.3 to up to 2.4 and the chemically determined gel content. And there is different curves for different bills of materials, so they combine different EVAs with different backsheets. And the first thing you can see is that all exhibit a kind of similar correlation, similar but slightly different. So again, that means you do need some calibration if you want to have a precise value for your gel content. But if the differences are not too significant, you can get a first idea just from the LXM number already. Another nice thing that was observed was that due to the fact that the only thing the operator does is pulling that handle, the distribution of the gel content result got much tighter when Q-cells switched from SOXLET to Crosslink testing. So they had a much better insight into the quality of their encapsulation after switching from one method to ours. So now let's look onto further applications. And I also saw the question about polyolefins, which will be answered right here. So obviously we're not in the year 2014 anymore, and polyolefin has become a very important material. And this is to show you that it also works for cross-linking polyolefins as encapsulant. So what we see on the left-hand side is again the result of a 9-point measurement on a 1-cell mini module after 15 minutes of lamination at 30 minutes of lamination, and both are shown on the same color scale for LXM, and you can see that it clearly shifts towards the red, so towards high values after 30 minutes of lamination compared to 15 minutes of lamination. So yes, it is sensitive to polyolefins as well, and it can be applied here. Same is shown here for 3 different pairs of 2 modules each with the same polyolefin encapsulant, but laminated with different backsheets. So you have to read it from left to right. So this is one bill of material, another bill of material, and a third bill of material, each for 15 minutes, 2 twin modules tested each time. and then the same pairs laminated for 30 minutes. And as you can see, there is for each bill of material a significant increase with lamination time. So it's always sensitive to the changes in the degree of cross-linking, also for the polyolefins. But what we also learn is that the backsheet does have a big impact. So if you want to measure very different modules, you need to make sure to properly calibrate for each bill of material in order to have to be able to make a decision about the quality of your degree of cross-linking. Here are just some examples of LXM distributions that we obtained in full maps of the PV modules. So the most intriguing one is the one you can see on the left-hand side. This was a series of, I think, in total 100 modules that were produced one after another. And it started out with very unsuspicious LXM distributions. So everything around a value of 1.4, which is quite normal for EVA. And then all of a sudden, we saw an decrease in LXM, but only very locally. The reason was that actually one heating element in the laminator broke down. So we had one very local cold spot, which resulted in very low LXM values, so very low degrees of cross-linking in that particular area. And the values are so low that for EVA, this is pretty much a clear failure in the field later on. And as you can see from the distribution, you would have to be very lucky to catch that by chemical sampling. Other distributions that we quite frequently see is something like that. So we have one corner that's very well laminated, and then the opposite corner or edges are much weaker laminated. This is usually caused by a 2x2 configuration in the laminator, where you tend to have cold edges and a hot center, and then you end up with a structure like this. Please note that this in the bottom here is just an illustration. It's just obtained by mirroring this pattern here to give you an idea where that comes from, but obviously it's not that symmetrical in reality. Another typical example is something like this here, that we have cool edges all around the module and the hot center in the module. This is particularly the case for slightly bowed modules, which then have different contact to the heating areas. So now the question is how you would apply a measurement like this. Usually when we talk to customers, in the first place, they always ask for an inline method because they want to tell their customers that they do a 100% control. And this is usually quite tough discussion because, again, remember that humidity will always find the weak point. So it's not that important to test every single module, but it's much more important to do a full map once in a while. So our strategy is usually to recommend to start with a manual tool, do a sampling maybe once per shift or maybe several modules per shift or once per day, but do measure one full map every once in a while. Give this feedback to your production, tune your laminator to make sure that you have a homogeneous distribution. And this is much more important than having an inline measurement where you would have to decide how many and which points to actually measure. And even if you would spend quite some money and go for 5 measurement heads, like one in each corner and one in the center, you would still miss like 90% of the module. So even this would not guarantee you that you catch all of the defects. So again, start with an offline tool, do a full mapping once per shift. And if you're happy with that and you get a feeling for your weak points, we're very happy to also equip you with an inline system, but that's actually more like a marketing argument to tell your customers that you do a 100% production control. The important part is the mapping once in a while. So I've also seen a question about glass modules. So let me come to the different scenarios that we have into today's PV module production. The most obvious approach would be to really take a module from production, cut out pieces, do the Soxhlet analysis, and wait for the result, which usually takes 12 to 24 hours while your production is ongoing, and then hope that everything goes well and continuing production afterwards. However, margins are so tight that nowadays this is not done anymore. So people, even for backsheet modules, usually tend to work with mini modules, which they just produce as twins of their actual production modules and cut out pieces of those in order not to waste cells and modules on the full scale. So they test those small mini modules, do the boiling and the Soxhlet extraction, wait for some hours, have to dispose the waste afterwards. Whereas in the case of backsheet modules, you can skip all of that and just use the tool on your ongoing production modules. You will get a first feedback after a couple of minutes and a full mapping after roughly an hour with no waste having to be disposed afterwards. So again, we're talking about feedback time of several hours versus some minutes. We're talking about local testing versus full mapping, and a lot of chemicals you have to deal with or not to deal with. Now let's come to the glass models. Again, if you want to do it perfectly, you would have to do like a core drilling in your glass module, extract the core, make sure that it's not getting too hot to actually impact the measurement by post lamination. Then again, wait for hours, do the disposal, and get the result. Again, this is way too much effort and way too expensive. So even in that case, people tend to use mini modules, which they produce as twin modules of their glass modules, but equip them with backsheets. So they run them in parallel, determine some kind of offset, which they have in lamination quality between the glass and the mini module, and then use that as kind of a monitor for their production process for the glass modules. So that brings us to the position where we can basically apply all of the advantages that the Crosslink tool has over the chemical extraction, that they also apply for glass production, because people have to produce those mini modules anyways. However, in the case of the Crosslink tool, they won't have to wait for several hours, and again, they won't have to deal with any chemical waste. They would not even have to cut anything out of the mini modules, but could directly go for measuring them in the Crosslink. So I won't repeat all of that again because I already said it. Again, it's the feedback time and the waste disposal that makes the difference here. This is now a very busy slide, and I'll be happy to provide it afterwards, so you can plug in your numbers. But I would just briefly want to stress the economic value of such a metrology method. So basically, what you have to take into account either the value of the PV module that you destroy, or the effort for producing the mini module that you produce as a twin, the cost for the Soxhlet analysis, which can easily go up to 100 to 200 euros per sample, depending where you are in the world, or even more if you have to send a full module to an external measurement entity. And if you compare all that to the non-destructive analysis, and even ignoring all the risk you take out of your production because you're now doing a full mapping and you don't have any ongoing production. If you take all this into account and assume that you sample about one module per shift, this will bring you to a return of invest of several 100% after 1 year, and to a payback period of, depending on the sampling mode and your actual costs, somewhere between some months and a very low number of years. But this would assume that you only test one module per week, which would be like a really courageous approach. So this really pays off, and it really comes up with a very low payback period in order to get your cost out of the system. And again, this ignores anything that has to do with waste disposal, chemical lab running, and all the risks that are associated with the chemical testing. Now, as a last point, let's come to the application of the tool for the assessment of PV modules with unknown bills of materials, which would be a typical scenario for maybe developers that are building a PV site anywhere where they have to use several hundreds or several thousand modules. And most of the time, they might have known which module they ordered, and they might have some idea of the bill of material, but they cannot be sure that if it's really the bill of material they ordered, and they will very often not know the particular materials in the module. So in that case, we think there is still some value in the module in the system, because I think you can always start with the assumption that a low homogeneity in the LXM distribution is always suspicious, whereas a high homogeneity is very likely to be completely in spec, because usually manufacturers are not idiots, but do their best to provide good quality. So it's very unlikely that they produce a homogeneous module which is out of spec in all areas. And a good example you can see on this module on the right-hand side here, where we did a full map. This time it's a half-cell module, so there's a lot of measurements being done. And what we see is a very inhomogeneous distribution of the LXM values, ranging from 1.5 to more than 1 in the maxima. And what is also marked here is the typical chemical extraction sample positions. So these were the areas where the material was usually cut out and sent for Soxhlet testing. And this, of course, for us is a very nice example, because it shows that you're really playing a lottery here. In that case, the cutout pieces, just by coincidence, resemble the most well laminated areas. So you would probably get a very good result of 1 point something from your chemical testing, but you would completely miss out on this part, which will be critical in the field. So what we would recommend, if you are using a lot of PV modules of the same kind and you want to make sure that quality is good, get a tool like this and do the homogeneity measurement, maybe like 1 module out of 10 boxes or something like that. And then look if you have homogeneous quality, and if not, mark the positions of the minimum LXM values of the minimum degree of cross-linking and send those samples for chemical testing, because only by that you can make sure that your result will be representative and will ensure you that your quality is okay. And that already brings me to the summary. So with the Crosslink, we think we provide a tool that determines the degree of cross-linking for PV module encapsulations in a very fast, possibly automated and non-destructive way. You get precise information which goes beyond the gel content testing. You can do full maps of the degree of cross-linking, even in the case of unknown bills of materials. You can use it for any cross-linking encapsulants, so it includes polyolefins. In principle, it's applicable inline and at-line or standalone. However, we do recommend to start with the standalone version and do the full mapping. And therefore, we think it's an ideal process control for quality assurance of the PV encapsulation quality. And that brings me to the end.
Visit Sinovoltaics.com to learn more.